Good morning. We are back. Another day, another chapter. So today we're looking at chapter 23, and we've been looking at electric forces and electric fields, and now we're going to move on and introduce two additional topics, and then we're kind of done with this foundational work. The two new physical quantities we want to introduce in chapter 23. The first of these is called the electric potential. Now, electric potential, I'm guessing you haven't heard of that, or it may not be very familiar, but the units that we measure electric potential in are called volts. And I'm guessing you've heard the word volts. So maybe that's the best way to start out, is to think in terms of what units are we working in terms of. Now, in addition to electric potential in this chapter, we're going to be introducing something called electric potential energy. Now, that should sound kind of familiar, because back when we did gravitation, we looked at the gravitational force in nature, we defined a gravitational force, a gravitational field, and a gravitational potential energy. So, remember, we looked at, in chapter 21, we looked at the formula we're using for gravity and the formula we're using for the electric force, and there's a very close analogy between those two. So whatever we've done in terms of gravitational definitions, we should be able to come up with the same physical quantities for the electric force, and that's what we've done. So again, just a quick review here. We've looked at electric forces, electric fields, and now the other two that go along with that, the other two quantities, are electric potential energy. Now, electric potential energy is an energy, so it's going to get measured in joules, but kind of the new quantity that's less familiar is electric potential. Now, you may be asking, well, wait, in gravity, we never looked at gravitational potential, or maybe you're not asking that, but I'm asking that. It turns out there is a gravitational potential, it's just that we just didn't introduce it. We don't, the electric potential becomes really important. Let's think about this. Where have you heard the word volts? And you go, well, any kind of an electrical energy source, a battery, for example, is rated in terms of the number of volts. So the electric potential certainly comes up with batteries, and we'll take a look at that. Or if I'm plugging something into an outlet. Right? If I plug into an outlet, the standard outlets are set up so that we are plugging into a 120 volt alternating current outlet. And we'll talk more about what that all means. But you can see that our sources for electric energy are rated in terms of voltage. And so this is going to be an essential quantity. Okay, so the big four: force, field, potential energy, and electric potential. Let's list them in that order. Okay, here's a list of the topics in the chapter, but let's see, how should we define electric potential energy and electric potential? So let's say that we've got our old familiar charged plates. So we got some plates, we've hooked this up to some kind of a voltage source. There you go, right there. And so one plate has become positively charged, and one plate has become negatively charged. Now, we've talked about in the previous chapters the presence of an electric field. So we introduced the concept of electric field, and that an electric field would get established between these two plates. Now let's think of bringing a charge, and our default is to start with positive charges and ask how would positive charges be affected by all this. So we've introduced this region of an electric field, and it's uniform. That's going to keep the examples a little simpler. Some geometries are going to be easier than others, and the parallel plate's nice because we get a constant electric field. So let's bring a positive charge in, and let's place it near the positive plate. Now we know there's kind of two different ways of looking at what's going on here. What we can do is we can look in terms of all these positive charges here and all the negative charges here. Now, it hasn't moved over here yet, so we're at position A. that charge that we introduced is being pushed away from the positive plate, right? The forces, if we think in terms of force, there will be a force pushing the positive charge away from the plate, and then there's going to be a force from the negative plate pulling the charge off in that direction. So there's clearly going to be a force driving this positive charge from point A to point B. Now, if you think in terms of how forces behave, how the gravitational force behaves, that means that when the positive charge, let's start at point B, what would it take to take this positive charge and bring it back to location A? Well, I would have to do some work. I would have to reach in there and push on that positive charge and store up some energy. Now, when I let go, I get that energy back. The positive charge gets pushed over to the negative plate. So what we're going to do is say, apparently location A corresponds to a high amount of potential energy. Same way we defined it for gravity. And then position B would represent a lower potential energy. So it's just these relative amounts that we're thinking in terms of. Now that's going to get measured in joules, the potential energy at point A, and the potential energy at point B is going to get measured in joules, but however we measure this, we know that this represents more potential energy than this does. Okay, now along with that in this chapter, we're going to introduce potential, and for potential we use the symbol V. So U represents potential energy, V is electric potential, and we've got these listed right here. The electric potential is defined as the energy per charge. So I don't necessarily have to know how much charge is present in this object. I can take the charges out and define the voltage in terms of energy per charge. Now that would be joules per coulomb, and joules per coulomb go by the name of volts. Okay, so those are going to be the units on the electric potential. Now, the electric potential is defined to be higher in the region of positive charge and lower in the region of negative charge. And so for this example, the higher potential energy is associated with a higher electric potential, and the lower electric potential energy is associated with the lower electric potential. Now that's because we're dealing with positive charges here. But let's ask ourselves, let's write down a couple things first, and then we can ask what happens if it's a negative charge. So the electric potential is defined as the energy per charge. So the potential energy we can calculate as the charge, little q, times the electric potential. Or we can flip this formula around and say that the potential then would be the electric potential energy divided by the charge. And the unit of electric potential energy is the volt, and the volt's defined as 1 joule per coulomb. Now let's go back and ask ourselves what would have happened. Let me take the positive charges out. So I've taken out the positive charges. At that point, the definition of potential energy goes away. I don't have a charge there. I can't talk about the potential energy of anything. But we can still talk about the potential. So just the same way that even with no charges there, I can talk about the presence of an E field, I can also talk about an electric potential. So in that sense, the electric potential is similar to the electric field in that once we've set up a charge environment, we can define, or we can go in and calculate what the electric field will be, and we can calculate the electric potential. When we bring additional charges in, now we're able to calculate the force on those charges and the potential energy that those charges will have. All right, let's look at some examples of how this is going to work. This is just a reminder that all of this traces back to our original electric force definition. I brought back a slide from chapter 21 saying that it all comes down to a couple of charges and the force acting between those charges. Everything that we've done has derived from that. And then again, the analogy that the force formula for the electric force is completely analogous to the force formula for gravity. Now there are some important differences here, and that is that gravity is always attractive, and that the electric force could be attractive or repulsive, depending on whether we have positive, 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 negative, negative, positive, or negative, negative charges present. So we got to be ready for the difference in signs for the electric force. Now here's another analogy that we can draw then. So with gravitation, we did this. We said that if we have an object with mass m1 or an object with mass m2, and m2 is bigger than m1 in this example, for each of those objects, the force would be given by mg. It's a uniform gravitational field, and at every location we're going to have a force given by mg. Now, if the gravitational field were varying at different locations, this formula still works. Even if little g is varying, we can still calculate the force at any location by taking m times g. Now let's step away from the gravity picture and let's define a region where there's an electric field. Now here the electric field is uniform. We're using these two plates to generate a uniform electric field. Just like the units on the gravitational field were newtons per kilogram, there's an analogous set of units here, which are newtons per coulomb. This electric field is going to exert a force on anything that has charge to it. So what we can define then, at least for these positive charges, is we're going to start at higher potential energy and go to lower potential energy. The same way here, that for masses m1 and m2, we're starting at higher potential energy. If these objects are moved in the direction of the gravitational force, of the gravitational field, then the potential energy is going to drop. So there are forces acting on these positive charges, and what that says is this is going to be higher potential energy, but it's going to be lower on the other side. Let's write down some analogous formulas. The same way that in a gravitational field, an object with mass m experiences a force of mg, in an electric field, a charge of q experiences a force q times e. Now the difference here, which is important, the m's will always be positive. The q's could be positive or negative. So in this picture, it's possible that instead of starting with positive charges on this plate and allowing them to get pushed over to the negative plate, we could have negative charges where, if we're drawing the same analogy, we would start them at the negative plate, let go, and allow them to be pushed over to the positive plate. So for the negative charges, I draw the very same picture, but the force will be opposite to the direction of the electric field, and that's what that formula is keeping track of for us. Now the potential energy that we defined here was mgh. And similarly, the potential energy here would be given by QE, that's the force, times the distance. But the potential energy direction is going to depend on whether we have positive charges or negative charges that are moving back and forth in that region. Now, wouldn't it be nice if there was some way to define some quantity that didn't depend on whether we're placing positive or negative charges here? And that's what electric potential does for us. The electric potential is going to be higher in the region of the positive charge and lower in the region of the negative charge, regardless of whether positive or negative charges are going to be brought into that region. Okay, here are the big four. When we're looking at the electric force, what we can do is define an electric field and an electric force acting on an object in that electric field. Now the potential and the potential energies actually have definitions in terms of integrals. So officially, if I move in the direction of the electric field, the electric potential is decreasing. If I move in the direction of the electric force, the potential energy is decreasing. So these are how the four quantities are related. And then here's another couple of equations, how we can calculate the force in terms of the electric field and how we can calculate the potential energy in terms of the electric potential. All right, here we go. Finally, here's their example with the negative charge. So what we're going to do in this example is we've set up a region of electric field. Now this is an electron. It says a negative charge. If the electron is free to move from this plate. So what we've said is, okay, is the electron going to naturally get drawn to the negative plate, or is it going to naturally get pushed away from the negative plate? And the electric force is going to be pushing the electron in that direction. If the force is in that direction, then this would say that the electron starts off with higher potential energy and moves in the direction of lower potential energy. Okay, and they didn't write lower potential energy. Oh no, that part got left out. So down here it should say lower potential energy. Now electric potential can be defined independent of the charge that we've introduced. The higher potential will come in the region where, well, let's look at the electric field. The electric field is going from left to right, and that says that the potential is higher here than it is here. The electric field will always point in the direction towards lower electric potential, whereas potential energy decreasing is in the direction of the force. For a negative charge, the force is in the direction opposite to the electric field. Okay, so we're going to try and, I guess this is all being done with the negative charges. So what we're going to do is we're going to say that this location, we're going to go ahead and define that as 0 volts. So with electric potential, with voltage, we are free to define a certain location to be 0 and then measure all the other, or define all the other voltages relative to that 0 position. And so that's what we're going to do here. Let's say that this is at 0 potential and that point B is at 100 volts. And so the difference in voltage between the two sides is 100 volts. So this is actually at the higher potential and this is at the lower potential. Now notice we didn't have to even discuss the presence of the electron here. We could just say, hey, the higher voltage is going to be determined by the orientation of the electric field. If I've got an electric field going from left to right, then this is sending us in the direction of consistently lower electric potential. Whereas to calculate potential energies, what we would have to do is look at the direction of the force. And because it's a negative charge, the direction of the force is going from right to left. And so that says that point B is at the lower potential energy and point A is at the higher potential energy. So I threw some numbers in here. This was a difference of 100 volts. Here, what we're going to do then is say that point A, we're going to start here and define this as 0 joules also by taking Q times VA. And then when we put in Q times VB, because the electron is negatively charged, let's keep that minus sign in there. And that's going to give us a decrease in potential energy of Q times V. and that's minus 1.6, 10 to the minus 17 joules. So in going from plate A to plate B, the voltage goes up, but for an electron, the potential energy goes down. Okay, so again, I guess the bottom line here is when we're dealing with negative charges, we're going to have to stop and step through the problem a little more carefully, because the signs on the voltage and the signs on the electric potential energy will be opposite to each other. With the positive charges, we don't have to be quite as careful because the direction of voltage increase or decrease matches the difference in potential energy. The potential and the potential energy match for a positive charge, but they're oppositely oriented for a negative charge. Okay, all right. Let's talk about a battery, because this may be, these voltage sources, batteries and electric outlets, could well be the most important examples that we can work from. So if I've got a battery, and I forgot to put a switch in this, so let me open the switch and then I'll close it. Here's a battery. Batteries are running chemical reactions, and the chemical reactions are designed to move electrons onto the negative terminal of the battery. So what we call the negative terminal is where the chemical reaction is creating, or not creating, but moving electrons to that location. So electrons are released in those chemical reactions, and those electrons then push other electrons out of the way. So at the same time, the chemical reactions inside the battery are drawing electrons from the positive terminal. Now, if the switch is open, then there's no complete path that the electrons can move through, and that means that pretty quickly the chemical reaction shuts down. It can't continue to build up more and more electrons at the negative terminal. They've started to repel each other. Similarly, it can't continue depleting electrons from the positive terminal. But once the switch is closed, then there is a path for the electrons to make their way through the circuit. Now you might be thinking, my gosh, when we turn something on electrically, those electrons are just zooming at enormously high speeds, and that's just not true at all. For almost any type of familiar use of electricity, any type of an appliance that you plug in, what we're going to find in a couple chapters here is that the electrons are moving really, really, really slow. And you go, well, wait a minute, how does this light bulb get turned on then? Don't I have to wait for electrons from the battery to reach the light bulb? And you don't. For the light bulb to turn on, it just has to be that the electrons in the wiring at that location are in motion. And as soon as we close that switch on the circuit, all of these electrons will begin moving. Not fast, very slowly, but they'll start moving. So to a very good approximation, as soon as we close the switch, almost instantaneously, electrons are in motion all through the circuit. So as soon as we close the switch, the electrons that were already sitting there start moving, and that means that the light can turn on immediately, almost instantaneously. Even though electrons from the battery are going to take hours or days to get over to this location. Electrons are not moving very fast through everyday type of circuits. All right, so that's what happens in a circuit when we turn something on using this battery. How can we keep track of the energy that the chemical reactions are providing? Well, the chemical reactions are sending the electrons off with a certain amount of potential energy. Now, typically what we do is we define the negative terminal often. We use that as a reference point, and we set that equal to 0 joules by definition. Now, we don't have to pick the negative terminal, but that's often an easy way to set things up. So the way that would work then is, if I've defined this terminal to be 0, then the other terminal is at 12 volts because it's a 12 volt battery, let's say. So maybe it's a car battery, and this is my headlight, and so the car battery has 12 volts of electric potential available. And if we set this side to be 0 volts, then this side is at 12 volts. Now the important quantity here is the difference between these two numbers. So this actually we could write as a delta V. We can say that the battery provides 12 volts of electric potential. Now the electrons have a charge, negative 1.6, 10 to the minus 19 coulombs. So if I have 12 volts of electric potential multiplied by that charge, how much potential energy does that correspond to? And the difference in potential energy between points A and point B is going to be 1.92 10 to the minus 18 joules. That's how much energy each electron coming through the battery is given. So from the chemical reactions in the battery, they are able to supply those electrons with this much energy. Each one of them gets this much energy. Now if the voltage were higher, individual electrons would get even more energy. The electron's charge isn't going to change. So the electron charge is stuck at this value, 1.60, 10 to the minus 19 coulombs, but the amount of energy given to each electron is going to depend on what the voltage is for that particular electrical source, is the way it works. So in terms of energy units, certainly energy units are going to be joules. Ooh, but wait a minute, there's another energy unit that we're going to use from time to time that you want to get familiar with. These are called EV. Now sometimes they're called electron volts, but I think conceptually it's easier to think of them as just EV, where E is the fundamental charge. So in the same way that, well, let's just try this. What we could do is for the Q versus V, instead of saying the charge on the electron is negative 1.60 10 to the minus 19 coulombs, we could say that the electron's charge is just minus 1 E. And so that would be minus 1 times 12 volts, but now the units would be fundamental charges times volts, and those get written as EV. So that would say that the energy given to the electron is 12 EV. Now that's an easy way to calculate it because every electron is going to have a charge of E, and if we send it through a 12 volt battery, the energy it's going to pick up is 12 EV. But we have to be able to convert back and forth between EV and joules if we're going to work in standard units. Okay, here are some examples of voltages. And the higher voltage means that each individual electron or each individual proton or whatever charge is moving, it's going to be proportional to how much energy they receive. So during a lightning strike, this has thundercloud to ground. So a lightning strike, 100 million volts, that's quite a few. High voltage power lines look like they're up around 100,000 volts. Power supply for the television tube, of which we don't really use anymore. The TVs now are flat screens. Automobile ignitions, 10,000 volts. Let's see, household outlet is 120. An automobile battery typically is 12 volts. Flashlight batteries are 1.5. So you get an idea of the different voltages, and that has to do with how the voltage has been generated. If it's a chemical reaction, each chemical reaction has a certain voltage associated with it. Let's see. So here is an electron. Here's an example. What we're going to do is we're going to use these parallel plates. We're going to charge this one negative, we're going to charge this one positive, and that's going to allow us to speed up that electron. So the electron is going to go faster and faster and faster, right? We're going to have some kind of a high voltage source here, and it's 5,000 volts. So notice now that we're actually using this voltage to set up a positive and a negative region, and we're not even asking about what the electric field is necessarily, because many of the calculations can be done directly in terms of how much voltage or how much electric potential is there for a given situation. So what we're saying is that the difference in potential energy between the two plates is 5,000 volts. So what is the potential energy of the electron? And then how fast will the electron move? So let's say this too. So what's going to happen here is we let go of the electron. We're imagining the electron starting from rest, and then it's going to get accelerated. There's going to be a large force pushing on that a force pushing on the electron. It's going to pick up speed. It's going to go faster, 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 faster. Oh, look what we did. We made a little hole in that plate. So the electron's going to get going really fast, and then it's going to travel through that hole, and then it's going to drift. So once it's outside of the region, then it can just move at constant velocity. So this is kind of a picture that we have here. So whatever potential energy we have between point A and B, that is going to get converted to kinetic energy. And the kinetic energy, we can bring back our kinetic energy formula as 1/2 mv squared. And so, and here's an outline of what's going on in terms of the forces and the potential energies. And then here's a diagram keeping track of the electric field and the lower and higher regions of electric potential. So that's actually a good side-by-side comparison. As far as transferring energy in, we're really interested in this diagram. The electron's going to get pushed in this direction. It's going to lose whatever potential energy it had, and that potential energy is being converted to kinetic energy. Whereas in this picture, if we're just thinking in terms of the setup before the electron ever arrives, we can say here's the electric field direction, and that the electric field direction will tell us that this side is at higher potential and this is to the lower potential. Okay, now, I just want to say with electric potential, with voltage, you see these signs that say danger, high voltage. Those signs all need to be changed, because let's think about this. If I set up these two plates so that there's a 5,000 volt difference between them, is this plate more dangerous because we say it's at higher voltage? And actually that's a little arbitrary. All we're really saying is that there's a difference between the two that is 5,000 volts. So if I touch this plate, which is probably not a good idea, or if I touch this plate, which is also not a good idea, the risk isn't from the individual voltages themselves, but what the difference would be between this plate and, say, the ground that I'm standing on, or this plate and the ground. Or what I could also do is I could touch this plate and I could touch this plate, and that would, guarantee 5,000 volts difference. So it's the voltage difference that's the concern. So all those signs that say danger, high voltage should actually say danger, large delta voltage. So within that device, what they're warning you about is that there are different regions within that device where the voltage differences are really large. And if you accidentally touch both of those regions, you could be exposed to a large difference in potential. Or the other possibility is I'm standing on the ground, I'm in contact with the ground. If this plate has a large delta V compared with the ground, or if this plate has a large delta V compared with the ground, that also puts me at risk. So the risk is always large delta V's, not the specific V assigned to any particular location. Okay. All right, let's see if we can figure this out now. So the voltage we're using is 5,000 volts. The kinetic energy we end up with is going to be equal to the potential energy that we start with. So let's say that we start with 5,000 EV of potential energy. Now the EV are kind of fun units to work in terms of maybe, but I think I need to get that converted to joules. So I need to put in that standard charge of the electron, and that gives me 8 times 10 to the minus 16 joules of potential energy to work with. Now I'm starting out with the electron at rest, and so that would be 0 EV or 0 joules of kinetic energy. By the time the electron has moved to point B, it's accelerated, it's going really fast, all of that potential energy is now kinetic. So once I've thought through this process, I think the takeaway from all this is, you know, I really just have to find out how much potential energy I start with, and then say that the kinetic energy is equal to that amount. So once we've done this problem a few times, we can just say, hey, if it's 5,000 volts being used to accelerate the electron, then I'm going to end up with 5,000 EV of kinetic energy because the electron has a charge of 1 E. So we can move through these steps pretty quickly once we see that process a few times. So as the electron moves from point A to point B, the kinetic energy steadily goes up and the potential energy steadily drops. By the time the electron exits the region between the two plates, now it's got that 5,000 EV of kinetic energy and the potential energy has dropped to 0. How fast is it moving? For that we use k is equal to 1/2 mv squared. The speed will be 2k over m square root. Plugging all the numbers in, I plugged in the energy. Now the energy here needs to be in standard units. It needs to be in joules. And that gets divided by kilograms. The kilograms will cancel with inside the joule. We'll take a square root. That's going to leave us with units of meters per second. Those are the units we want. And so the electron's coming out at, the electron's coming out at a pretty good speed, right? This is a potential difference of 5,000 volts, and it's leading to a velocity. Now, velocities are little v, and electric potentials are big V. And now, don't get those mixed up. These are little v's, those are velocities. That works out to be 14% of the speed of light. Okay, and I think we may have mentioned before that as we approach the speed of light, these formulas are going to be not reliable anymore. We're going to have to use special relativity. And we'll get to that later in the course. Okay, so again, as just a reminder, if I've got a region with electric field lines, so that's the direction of the electric field lines, if I go in a direction that kind of follows the direction of the electric field lines, the specific distance that I've traveled through that electric field will tell us how much the electric potential has dropped. The drop in electric potential comes by following the electric field line. So I'm going from higher electric potential to lower, to lower, to lower. And the delta V's are going to be the important quantities. Now what's going to happen in terms of potential energy, if this is a positive charge now that we bring in, place at point A, and allow it to be pushed to point B, then the electric potential energy comes from following the force acting on that charge. If it's an electron, if it's a negatively charged object, how would that change? And if it's negatively charged, we actually would have to push the electron. The electron's being pushed in the opposite direction. And so we could start with the electron at point B and allow it to travel in the opposite direction if we want it to acquire more and more energy. All right, so the pluses and the minuses we have to think of in kind of reverse direction here. Let's see how we are doing with time. All right, so we do have some time left here. Let's keep going. So the relationship between the electric potential and the electric field, simplest example would be a uniform field. If we have a constant electric field that we have here, and here they're using a positive charge, so the location of potential energy, high potential energy, matches high potential. The potential energy is equal to force times distance for this. The force is equal to potential energy divided by distance. The potential is E times D, or flipping that around, the electric field can be calculated as V over D. So that's the simplest case where we have a uniform electric field. So let's figure out what the electric field is in this example by the voltage. So now, instead of saying what the charge is on the plates, for example, what we're going to do is start out with voltages. So I've got some plates. We're hooking it up to a voltage source where there will be a difference of 50 volts between the plates, and the separation between the plates is 5 centimeters. So the way that would work is we would say, okay, switching from electric potential to electric field, the voltage is 50 volts. The distance here is 0.05 meters. And what we just showed is that for a uniform electric field, the electric field is equal to the voltage, the electric potential, divided by D. I can take the 50 volts, divide through by, now that was centimeters, so I had to convert to meters. That's going to give me an electric field that is 1,000 volts per meter. Now an equivalent set of units is newtons per coulomb. We've been doing most of this in terms of newtons per coulomb. But volts per meter is another kind of reasonable set of units maybe to work in terms of. And what's nice about volts per meter, it says that for every meter that I follow this electric field, the electric potential is going to drop by 1,000 volts. It's kind of saying how concentrated the electric field is. So, so that's what we've determined with the electric field. Now what would happen if we did this? Let's keep the two plates attached to a 50 volt source, but let's make the distance shorter. Well, the voltage is still 50 volts, but the distance is shorter, and that would give us a larger value for the electric field. Okay, and that's often the way things are working. It turns out that we have a certain voltage source for the two plates, and that means that the voltage is fixed. I can move the plates farther away from each other if I want a lower electric field, or I can allow the plates to be closer to each other if I want a higher value for the electric field. Okay, once in that case the voltage has been fixed. Here's another way of thinking about what's going on here. As we move from one side to the other through a uniform electric field, the voltage is steadily dropping. If I decide to say that this side is at 50 volts and this side is at 0 volts, then what we would see is a steady drop, 50, 40, 30, 20, 10, 0, and that was 5 centimeters, right? So for every centimeter I move through here, the voltage will drop by 10 volts. Okay. So that's a way of thinking in terms of what we call equipotential surfaces. I'm crossing the 40 volt surface, I'm crossing the 30 volt surface, 20, 10, and then when I reach the other plate, that one's been designated as our reference at 0 volts. Okay, now we've been looking at some examples where, quite a few of our examples I think have been uniform electric fields. What happens if the electric field's not uniform? What if we have a sphere of charge generating an electric field? Well, what we want to do now is calculate the electric potential at regions outside the sphere, right at the surface of the sphere, and then at regions inside. Now this takes us back to chapters 21, and actually more so 22. where we were using Gauss's law. And by using Gauss's law, we were able to come up with a formula for the electric field in the outside region, and then an electric field on the inside region. And then the two formulas that we came up with matched right at the surface. So let's go in and see how we would determine the electric potential for this setup. Okay, so here is the sphere. Now we're going to look at two of these examples. The first example is when all the charge is at the surface. And then we'll come back and we'll redo the example where the charge is spread uniformly throughout the entire sphere. So again, we're going to start off with all of the charge evenly spread along the surface of the sphere. We'll say that the sphere has a radius of big R. Now what I'm going to do is I'm going to take little steps in little r, dr, 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 dr. And the reason for that is if I'm outside the sphere, if I'm outside the sphere, the electric field is given by kq over r squared. So that's telling us what the electric field looks like outside the sphere. If you remember from chapter 22, the electric field inside the sphere is zero. It exactly cancels out if all the charge is on the surface. And so the electric field in here everywhere is zero. Now, sometimes students imagine, well, if the electric field is zero, then the potential has to be zero at the same time. And that's not true. So if I'm in a region where the electric field is zero, what that tells me is that the voltage is constant. But the voltage is not necessarily zero. Voltage is determined differently. So voltage is kind of like potential energy. It's kind of an accumulated effect of following the electric field line. So for example, let's say what we've got here is there's no electric field inside, and then outside we do have an electric field directed away from this positive charge. What that tells me is that I can start out here at infinity and work my way inward. That's what we did with potential energy. If you remember, we defined potential energies to be zero when objects are infinitely far away from each other. And that's what we do with electric potential also. So we follow that same convention. So I'm going to start out here and say the electric potential out here at infinity is equal to zero. And then if I start moving in this direction, the question becomes, is the potential energy increasing or is the potential energy decreasing? And if I'm going uphill against the electric field, then the potential is going up. So as I approach a positively charged object, the potential just keeps going up. So by the time I hit the surface, I'm going to have some amount of potential energy. Let's just think in terms of potential. So the electric potential will be some positive value. Now let's flip this around and say that this is negatively charged. Well, if it's a negatively charged object, again, out here we start at zero. But this time, instead of going against the electric field, I'm following the direction of the electric field towards the surface. As I get closer and closer to a negatively charged object, by definition, the electric potential is negative. So for positive objects, the potential is positive, and for negative objects, the surrounding electric potential is negative. Okay? And again, the signs are just arbitrary as to what we've called positive and what we've called negative. So now I can carry out this integration of the electric field. I'm going to say this very quickly, is kq over r squared. Integrating kq over r squared leaves us with kq over r, and that's the formula. If any of you guys want to see this in more detail, we can take a look at it, but we're mostly interested in taking these results and working from that. So what that tells us is that The electric potential at any location outside the sphere, at point C for example, the electric potential is given by kq over r. Now if q is positive, then this will be a positive number. If q is negative, it'll be a negative number. And again, the positive and negative just is referring to whether we're getting closer to a positive charge or whether we're getting closer to a negative charge. And this all traces back to Benjamin Franklin, who was kind of America's first physicist. And Benjamin Franklin did a lot of experiments with electric charge and kind of defined what we mean today by positive charge and negative. He could have made the opposite definition. He could have switched and said what we call positive now is, could have decided to call that negative. So again, the signs themselves are just keeping track of whether the charge source is positive or negative. It doesn't mean anything in terms of how much voltage. The amounts are going to be the same, whether or not it's positive charge or negative charge. Let's see, so this is our general formula for the electric potential outside a spherical object. So just like the electric field was kq over r squared, the electric potential is going to be given by kq over r. Now both of those formulas say when little r becomes infinitely large, the electric field will go to 0 and the electric potential will go to 0. So out here at infinity, the electric potential is 0. Now as I get closer in, when I get to the surface, when I get to point B, I will have an electric potential of kq over r. So that's the same thing as this right here, kq over r, where r is the radius of the sphere. Now, when we think about this, let's see, what's going to happen right at the surface is going to be kq over big R. Now there's no electric field inside. So what I've done is I've climbed through this electric field all the way up to the surface, but once I get there, there's no more electric field to work against. So what will the voltage inside be? And the voltage all throughout the inside will be the very same value of whatever we had accumulated by the time we reached point B. So you can kind of think of this as climbing that mountain, right? The potential is going to, and here it is, the potential is going to be increasing, increasing, increasing right up to that ledge, and then it turns out that there's just a plateau at the top. There is no electric field, and that means that the electric potential remains constant. It doesn't go to 0. And so the difference in electric potential between point A and point B, the difference is 0, and that's because point A and point B have the same electric potential, not because it's 0. Okay, so that's how the electric potential and the electric field are going to be set up surrounding our sphere. Now, what happens if we charge the sphere? Now, everything is going to be identical all the way up to the surface. Oh no, I labeled A, B, and C differently. So, let's see. This was C, right? And this was B and A. So this time, when I start all the way out here, outside the sphere, the formulas have not changed. And we learned that back in chapter 22 when we were looking at Gauss's law. And we saw that if it's spherically symmetric and it's the same amount of charge, we're going to have the same electric field outside. Well, we're going to have the same formula for the electric potential. At the surface, we're going to have the same value. What happens inside? And it turns out that inside, the electric field dropped off like little r over r. If you go back and look at the example from chapter 22, you'll see that we've derived this. That means that the electric potential then is going to have to increase, because when I go from A to the center now, I am working against an electric field. So the potential is going to be higher at the center in this case. So that's kind of interesting. By having the charge spread uniformly throughout, I'm going to end up with a different value for electric potential at the center. It's going to represent a different amount of potential energy moving through that differently distributed positive charge. Now there's a lot of detail here, and I'm going to go through this quickly too. To calculate the difference in potential energy between, let's say, point C and point A, we can integrate the electric field. The electric field was inside is this value. When I integrate R, I get 1/2 R squared. I evaluate that between R and R, and it says the difference in potential from point C to point A, here, this region right here, is going to be given by this expression. So in order to calculate the potential at point C, I'm going to have to start with the potential at point A and then add on this additional potential that we calculated. There are two different regions having two different formulas for the electric field. So going through the outer region gave us this amount, kq over r, and then going from A to C meant integrating with a different electric field, and that gives us a different formula. Now what we can do is algebraically combine these, and let's just look at the results. What it tells us is, again, at the surface, the electric potential will be kq over big R. But as we move inside, the formula is more complicated. Now, what would the potential be right at the surface? Well, at the surface, little r equals big R, and this would be 3/2 minus 1/2. I'm getting the right formula at the surface. What would happen at the center? And right at the center, little r would be 0, and that says that the potential goes up to 3/2 kq over r. So at the surface it was kq over big R, but at the center it's going to be 3/2. It's going to be 50% larger at the center compared with what it was outside. And so here it is, our sphere with charge uniformly spread through. Outside, the electric field, just the electric field, looks the very same, but inside the electric field gradually linearly drops. What's going on in terms of potential is that we're still getting this 1 over r, kq over r formula here, but when we go in, we're still working against the electric field, so the electric potential continues to climb. Okay. All right. That is, well, this is kind of a follow-up, I guess. This is going back and looking at some carefully drawn graphs for the case where all the charge was at the surface. The electric field comes right up and then it drops to 0, and it's 0 everywhere inside. In terms of the electric potential, we have this increasing electric potential right up to the surface, and then inside, because the electric field is 0, V remains constant. So that's kind of our plateau in terms of electric potential. Okay, that's probably a good place to take a break. So let's stop and take a break.